Hello, this is Dr. B, topic 2.3 for AP Chemistry, structure of ionic solids. Ionic solids. The objective is to be able to represent an ionic solid with a particulate model that is consistent with Coulomb's law and the properties of the constituent ions. Ionic solids consist of positive ions, negative ions, so cations and anions. Discrete ionic molecules do not exist. Instead, you have a repeating array of molecules that are held together by strong Coulombic forces, ionic bonds, between oppositely charged ions that are adjacent to one another. The following properties are due to this arrangement. Ionic solids are non-volatile and have high melting points. Ionic bonds must be broken to melt the solid, which separates oppositely charged particles. This requires very high temperatures to give the particles enough kinetic energy. They do not conduct electricity when they're in solid form. The charged ions are in place. When they are melted or dissolved in solution, the ions become free to move about, enabling electrical conduction. Many ionic compounds are soluble in polar solvents like water and insoluble in nonpolar solvents like benzene. The relative strength of different ionic bonds can be estimated by using Coulomb's law. Coulomb's law, remember, it states that the force is proportional to each of the charges and inversely proportional to the distance squared. Therefore, calcium oxide, 2 plus and 2 minus, has a much stronger bond than sodium chloride when it's 1 plus and 1 minus. This manifests in melting points of each compound being different, as is shown here. Similar reasoning can be used to compare ionic compounds with varying internuclear distances. For example, because chloride is smaller than bromide, sodium chloride has a higher melting point than sodium bromide, as shown there. Increasing the distance between charges reduces the strength of the Coulombic attraction. So why does KBr have a higher lattice energy than Ki? Bromide ions have a smaller ionic radius than iodide ions. This results in a smaller distance, between the potassium ion and bromide ion. The smaller distance increases the Coulombic attraction, resulting in higher lattice energy. Draw a particle diagram of rubidium iodide. Be sure to include relative sizes. The first thing you need to be mindful of is what is the formula for rubidium iodide. So we know that rubidium has a 1 plus charge and iodide has a 1 minus, so therefore the formula is going to be RBI. There's going to be one of each ion present. So remember that atomic radius tends to decrease in size from left to right on a period. And remember that rubidium forms rubidium ion by losing one electron. Therefore, it loses its valence shell. Therefore, a rubidium ion is going to be smaller than a rubidium. Something to be mindful of because it mentions making sure to include relative sizes. The iodine, forms the iodide ion by gaining one electron, thus increasing the electron-electron repulsions and increasing the ionic radius. Therefore, the iodide ion is going to be larger than the iodine. So, let's do rubidium ion will be less than a rubidium, and then an iodide ion will be larger or greater than an iodide. The reason why I bring this up is because from left to right, you have rubidium and then iodine on the same period. So how are we going to draw out our diagram? So a particle diagram or particulate diagram is a sort of like a microscopic, macroscopic, drawing that represents ions or molecules in solution interacting with each other, etc. So to draw a particulate diagram or particle diagram of an ionic compound, you need a few things to make it correct. You need alternating plus and minus, and like the ions, and you have to make sure that the relative sizes are there. So if we know that, let's say if this is rubidium, and then iodine is going to be here, like this is a regular one, then we know that rubidium iodine, a rubidium ion will be a little bit smaller because it's going to lose a valence shell, and the iodine is going to be a little bit bigger. Then we have to make sure that we kind of keep these consistent. So you should probably have a what you call it. If we're going to draw something, we need to keep. That's what I'm going to tell you. So let's say this one is going to be kind of bad. Rubidium is going to be shaded in like this, and then iodide is not going to be shaded. So my drawing will be in the empty space. So we need to make sure that we are alternating, and we're doing our best to maintain the relative sizes for our ions as we are drawing them. It doesn't specify how much of each you need, but sometimes it will be specifically asked of you to have this correct proportion, correct number, etc. So that's something you need to be mindful of when you're reading your questions, and you'll see some of that in your homework, and you'll see something similar in FRQs and MCQs. All right, that's it for now. If you have any questions, let me know.